Alright, so for part B, we're going to continue on with NMR, and we're going to look at carbon-13 NMR. So previously we looked at proton NMR, which gave you all kinds of information. We can also look at carbons, and these can make it easier to determine the total number of carbons. And these are usually decoupled, which means that in most of the carbon spectra, your peaks will appear as singlets. So you can see a spectra here. These are all singlets. So each signal on a carbon-13 NMR spectra represents a carbon with a different environment, just like protons. So if we have this 1,2 substituted benzene, we're going to see 1, 2, 3, 4 different signals. When you have the 1,3, we have 5 signals. And with this one here, we have 3 signals. So all of the dotted lines are showing you the axis of symmetry, which makes the environments the same for this carbon as it is for this one. The proton NMR chemical shifts from 0 to 12 for proton NMR. For carbon, it goes from 0 to 250 ppm. But the pattern is the same, where you see the ketone, aldehyde, carboxylic acid. The more electron-dense carbons are down in the further range, and lower down are the CH2s and CH3s down here. So again, this is another table you don't need to memorize. Carbon NMR gives you different signals. There's something called depth C13 NMRs, which tells you what type of carbon is present if there's protons attached to them. The top one here is the normal carbon NMR that you would see. So your CH3s look like CH2s, which look like CHs and then carbons. But if you do a depth 90, only CHs show up here. So you can see where CHs show up. And then if you do a depth 135, the CH3s will stick up from the spectra. CH2s go below the line and CHs go up. So you can determine where your quaternary carbons are, where the absence of these are. You can see where CH3s are, CH2s, and then CHs. In this spectra here, you have to determine the structure of an alcohol that has a molecular formula of C4H10 that has the following spectra. This one, if you look at the formula, happens to have 0 RDBs. And if you look at the broadband, there's 3 signals, so we should have 3 types of carbon. And from the formula, there's C4, so we probably have symmetry somewhere. So there's going to be 2 that are the same. If we look at the depth 90, and if you refer back to the slide just previously, the depth 90, the CHs are the only ones that show up there. So this one is a CH. From the depth 135, the protons on the carbons that are CH3 or CH are positive. So we know this is a CH, which means that this one is a CH3. And the ones that dip below are CH2s. So we have a CH and a CH2 and a CH3, and this is probably the symmetry here, and we have an alcohol. So that would be a structure that we can draw that fits the formula. These 2 CH3s are the same, which is why we only have 3 signals. There's the CH, which is right here, and then the CH2, which is here. So that's how you can use depth NMR. So if we put all of the pieces together, we deduce the structure of a compound with the molecular formula C5H10O that results from the following IR, and then the NMR spectra are on the other one. We also see mass spec, so this is just telling us that the mass is 86, but we already have the formula, so we don't necessarily need that. So the first thing you want to do is find RDBs. So this would be 5 times 2. So we have 1 RDB. If I look at my IR, there's no carbonyls. So that's not the source of my RDB. I do have a CH here, sp2. So I probably have some sort of carbon-carbon double bond. So if I look at the spectra here, I can go and here I have 1, 2, 3, 4, 5 types of carbon. And my formula had 5 carbons. And the formula was C5H10O. So there's no symmetry there with respect to the carbons, and these are the proton NMR. So at 1.2, we have a proton that integrates to 3H. That's what those numbers are there. That's a triplet. So we have a CH3 next to a CH2. At 3.5, I have 2H, the quartet, CH2 next to a CH3. This one's a doublet. This one looks like the doublet of doublets. So the doublet of doublets, we have a CH2 alkene, and that's going to be next to a CH1. The double bond will split them, and I have doublet, which is 2 minus 1, so it's CH. And then at 6, we have 1H, and that is kind of a multiplet. So that's the CH next to the other CH2. If I add up, I have 3, 6, 7, 8, 9, 10. 10 H's, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 C's. So we're just missing an oxygen now. So the pieces that I have, this is probably one alkene. So I have a CH2 next to a CH. So there's room for something here. The CH3 and CH2s are the same. And then we have another CH2 CH, and I'm missing an oxygen somewhere. So if I look at my puzzle pieces, I have a CH2 next to a CH, a CH3, CH2, CH2, CH. I have 5 carbons here, but I have 1, 2, 3, 4, 5, 6 here. So I'm going to assume that this CH is the same as that one. That'll be a little bit easier to put my things together. So I have an oxygen here. And if I recall, oxygens, or these protons that show up between 4 and 3.5, are ones that are in the middle of an ether. So these hydrogens on the carbons are probably in between an oxygen, which is this CH2CH3, and this CH2CH. And that CH is the same as this alkene CH, which is next to a CH2. So that is the structure of that. So we use the oxygen, CH2CH, that one, and this one. So in a less ugly drawing, we have CH3CH2, oxygen, CH2, CH, CH2. So if you've ever heard of MRI, it's magnetic resonance imaging, which are almost the same as proton NMR spectrometers, except that the body is analyzed rather than a sample in an NMR tube. So different tissues have different concentrations of protons, and the MRI can give 3D images of all those different tissues based on the different concentrations of protons. So when you're getting an MRI done of your knee, it's the same thing as getting an NMR of your knee.